Now coming to the shape of the different orbitals. Now you know that here psi is known as what? This psi. Psi has got no significance in the Schrodinger wave equation. The psi. Psi has got no physical significance, so to say. Got it? So it gives the orbital wave function. But when I take psi square, got it? Then it gives a probability of finding an electron. Got it? It gives a probability of finding an electron. So and this particular one has got a significance. But psi, which is nothing but known as an orbital wave function, which is simply called as wave function also, has got no physical significance here. But psi square has got the significance because it gives the probability, the electron probability of at a particular point, we can say that. Clear? Or electron probability density at a particular point. So here we are involved with psi. If you do the what you can with psi square, if you do with psi, then it has got no physical significance, so to say. Alright, but for 1s orbital psi it is the same. But for 2s orbital, if you do it, then you will see that the graph goes down here. I'll explain you why it goes down here. Alright, first let me explain this particular one. Now, what you find is here that as the distance from the nucleus increases, this is the radius. The distance from the nucleus increases, the probability of finding an electron decreases. You can see. This is for the 1s orbital I have done it. As the distance from the nucleus is increasing, the probability of finding an electron is decreasing. Fine, this is very simple. So hence, what you find is that is nothing but in case of 1s orbital, if you show it, you can show this particular one in this way, that this is for the 1s orbital. This is for the 1s orbital. We can show. So what we find is that it is spherical in this way. As the distance from the nucleus, as I said you, it's increasing, that is radius is increasing, the probability of finding an electron, the graph you can see it is decreasing. So hence we can show it that this particular 1s, this is 1s orbital, is spherical in shape. So it is nucleus in between, and that is the distance, what you can say is decreasing. Distance will decrease then only, we can show it then only when the graph will be this sort of. Now it cannot be a parallel line, it cannot be a vertical line or a horizontal line, isn't it? It is in this way only, because you see the graph here. It is gradually decreasing. Here also see the line, gradually it is decreasing. We can say that. So in this way, it has been seen that as the distance from the nucleus is going to increase, see the distance is increasing from the nucleus. Here you can see distance is increasing, and the probability of finding an electron is decreasing here. I think it's clear. Now, in case of 2s subshell, what do you find? As the distance is increasing, the probability decreases, and it reaches a particular point where the probability of finding an electron is 0. And what is that called as? Node. That is known as node. Again, as the distance increases, again the probability of finding an electron increases, and again it decreases further. We can say that. So here, what we find is that we have got a node here, but we don't have a node in 1s subshell. Alright, in 1s subshell you don't have a node. Alright, you can't see a node here. But here in case of 2s, what we find is that as the distance is increasing, see here, the probability of finding an electron decreasing, and it reaches a particular point, it touches the x-axis, where the probability of finding an electron is 0, because this is I square gives the, I already said you, probability of finding an electron. So hence it becomes 0. So what is that called as? That is known as the node. And again, as the distance increases, further probability increases, and again it further decreases. So if you want to show this one, what you can say, this way, in this electron dot diagram, if you want to show it, then what it will be? So this is your nucleus, this is the probability of finding an electron, this is your 1s subshell. Alright, see, 1s subshell. Alright, clear? You can say that 1s subshell. Clear? This is. Now, after that, the probability becomes 0. Again, as the distance is increasing, again probability is increasing. So here, a particular distance you will leave it, where you will not find any electron at all. You will not find any electron at all. So this is that particular. So this one is your node. This particular distance is your node, which is shown here in the graph. Here it is that particular one. This is the node where the probability of finding an electron is almost nil or negligible. Again, you can see why the graph is increasing, because again the probability is increasing. So I don't have space here. Again, you will draw dots here. Alright, and again after that, what you will find is that to a certain distance, again here you will get it. That is, you can say, now this is for the 3s, because 1, 2, 3 subshell. Now I have done it here 2 subshell, 2s. In 2s, how many nodes you got it? 1 node. Similarly, 3s will draw, then how many nodes you will get it? 2 nodes you will be getting it. Alright, and what these nodes are called as? Spherical nodes, because the shape is sphere. We can say that. So it is known as the spherical nodes. We can say that. Clear? Now, for the P subshell, if you draw it, I hope you understood this particular one. Now, let me rabbit this also. I hope you understood the graph also here. So here, as the distance increases, you have seen distance increases, the probability of finding an electron decreases, then it reaches a point where the probability becomes 0, that is called as a node. Again it increases and again further decreases. In this way it goes on. Got it? And thus we know the shape of the S subshell, which is spherical in nature. We can say that. Clear? Here I have kept it ready. Now, in case of P subshell, how is a P subshell done? So this is your P subshell. You can say that in case of P subshell, we are having spherical nodes as well as angular nodes. So how many angular nodes we are having? One angular nodes. You can say that. In case of P subshell, one angular nodes is there. Let us say this one is X. So this is your PX. Let us say this is Y and this is Z. So in case of P subshell, we are having just one angular node. We can say that. Clear? In case of P subshell. Fine. There is angular nodes and the planar nodes here. Here. So this is known as a nodal plane. This one is a nodal plane. Three-dimensional now. This is a nodal plane. This is a nodal plane. We can say that. Clear? And this is your angular node. This particular point. So we are having a spherical nodes as well as we are having the angular nodes. Spherical nodes. You will say where it is spherical nodes, because this point it acts as a sphere. We can say that. This dot. Clear? So now this also is a dumbbell shape. It also similarly we can say this also it forms a sphere. This sort of we can say that. So we are having a spherical nodes as well as we are having the angular nodes in case of P subshell. Fine. Now in case of D subshell, so how many angular nodes we got it? One. See the diagram. Angular nodes is one, and this is known as a nodal plane. This particular one, where the probability of finding an electron is said to be 0. The plane or the surface, we can say that. Now, in case of D subshell, how many you will be getting it? You can tell me now only. You can, in case of D subshell, how many you will be getting it? Let us say dxy. This is your x axis. This is your y axis. So D subshell is double dumbbell. Double dumbbell, isn't it? That was dumbbell and P subshell was dumbbell and D subshell is double dumbbell. So how many nodes you get it? Two angular nodes. This is one angular node and this is another angular node. We are getting two angular nodes in case of D subshell, so to say. Alright, two angular nodes you got it in case of D subshell. Clear? So in this way we can calculate the number of what you can say the spherical nodes or the can be calculated for any orbital as n minus l minus 1, which I have given to you already. I have sent you a PDF. Now number of angular nodes is nothing but is your L, depends upon the azimuthal quantum number. So the total number of nodes will be what? N minus l minus 1 plus L. Spherical nodes plus angular nodes. So LL gets cancelled. So what we get it? N minus 1 as a total number of nodes in any orbital. Alright, clear. So in this way. Now this is, I said you, this is the nodal plane. This particular one is the nodal plane. Clear. We can say that. Clear. And this is the nodal axis, this particular one. Because in case of a sphere, alright, in case of sphere, this is a sphere, this is said to be S. Clear. And this is your nucleus. So the line, the imaginary, all these are imaginary, remember it. The line which passes through is imaginary, and this is known as what? Nodal axis, we can say that. Alright, now in case of 2s subshell, this is 2s, this is your node, we can say that. In 1s, we don't have any nodes. In 2s, how many nodes are there? That is nothing but one node. In case of 3s, one more will be there. How many nodes will be there? Two nodes. This is one, another will be having it. Alright, same this way. So we calculate the number of nodes and also we know the shape of the orbitals, we can say that. Clear? So now next is, after that is we can say this particular diagram which you are seeing, that is nothing but it's a plot for radial probability function. Radial probability function. Now listen here. What is the difference between Bohr's atomic model and what you can say the modern atomic theory? Alright, the difference between, in case of this probability of finding an electron, alright, between Bohr's atomic model and between the what you can say this modern atomic theory, what's the difference? What we will find, how to find the difference? So listen carefully, you may write it down. Alright, write it down. That is, the important difference between the Bohr's atomic model and the wave function model or the modern atomic theory lies in the fact that Bohr suggested that at a distance of 0.529 angstrom, alright, you will get an electron. uniformly. You will be getting an electron uniformly at a distance of, this is known as Bohr's radius, you know that, R0, which is 0.529 angstrom. Listen carefully. At a distance of 0.529 angstrom from that of the nucleus, you will get, that is uniformly the electrons will be getting it. Got it? That is said to be as what you can say the Bohr's atomic model at a constant, what you can say, distance from that of the nucleus, constant, which is for the first shell we can say that 0.529 angstrom. For the second cell into 2, for the third cell into 3, this value you will do it. Got it? Which I will show you to you here. Now, but the wave mechanical model or the modern atomic theory suggested that no, it is not in that case. The maximum distance where the probability of finding an electron is maximum is what you can say 0.529 angstrom. It is not a constant because it may shrink, the distance may shrink or distance may be more also, little bit, depending what you can say the waves, we can say that, depending upon the waves. So it is said that 0.529 angstrom from the nucleus, according to the what you can say wave mechanical model, the electron is most likely to be found. The probability of finding an electron is 0.529 angstrom. We can say that it's most likely to be found at this distance. Got it? At this distance, this particular which distance? That is 0.529 angstrom. We can say that. And there is probability of finding an electron at distance which is shorter than, got it, as well as larger than. I said you know when the electron is, when you are drawing the electron cloud. So in certain cases you can find the electron it is being found at distance 0.529 angstrom less than that. In certain cases you can find the electron which is 0.529 angstrom more than that. Got it? So you can find the electron less than that also, you can find the electron more than that. But the probability of finding the most, what you can say, the probable distance from that of the nucleus where the electron is most likely to be found is what? 0.529 angstrom. But Niels Bohr suggested that at a constant distance from that of the nucleus, what is that constant distance? That is 0.529 angstrom, the electron is being found, we can say that. At a constant distance, that means uniformly it is being found. But the modern atomic theory says, or the wave mechanical model does not say that. It says that the probability of finding an electron is maximum here. It means what? We can find electron beyond this as well as below this also we can find it out. That is the most important difference you need to understand. Alright, that is the difference between when you draw the shape of the S and the P and the D subshell, we can say that. Alright, now what is the radial probability? Now write that definition of radial probability. Radial probability is this: 4 pi square pi r square sigma psi square, 4 pi r square psi square. Got it? Acha. So where it has come from, I will tell you. First you have the definition. Radial probability function is that which gives, radial probability function is that which gives the probability of finding an electron, the probability of finding the electron, not an electron, probability of finding the electron at a distance r from the nucleus irrespective of any direction. At distance r from the nucleus, this is the distance r, we can say that, which is measured in angstrom, which is the distance r from the nucleus, we can say that, from the nucleus. Clear? Irrespective of any direction, we can say that. Clear? Now when you will find the derivative of this particular one, alright, now this probability radial function is denoted letter P here. P is equal to 4 pi r square sigma square. Now when we will find the derivative of P dr, so it will be nothing but 4 pi r square sigma square, psi square dr it will be. Alright, now the why do we what you can say psi square? I have said you already. The psi square gives us the maximum probability of finding an electron at a particular point, we can say that. I have told you already, psi has got no significance here. Psi is what? Simply it's a wave function, orbital wave function, we can say that. But psi square, what it gives you? It gives you the probability of finding an electron at that particular point. Clear? So that you must understand it. Fine. Now here, what we see is that if you consider the atom as spherical symmetry, according to Niels Bohr, if you consider it, it is more useful to discuss the probability of finding an electron in a spherical shell of thickness, what you can say dr, means what? C. We will consider an atom to be a spherical shell, C, it is spherical shell. Now the most, what you can say, this probability of finding an electron at a distance, what you can say, this particular distance is nothing but known as the dr. Now this is your r, this particular one is your r, this one, and this distance I will be taking to be as r plus dr. That means this distance is your dr, we can say, a small thickness, we can say. Okay, fine. Now in this way what you find is that what I said you, that as the atom is considered to be a spherical symmetry, as you can see it here, it's a spherical symmetry. Now that is, it is more what you can say, useful to discuss the probability function, probability of finding the electron in a spherical shell of thickness, you can see spherical shell, this is spherical shell of thickness dr. Alright, fine. And of thickness dr at distance of r from the nucleus. So total distance from the nucleus is r plus dr. So hence the volume of the spherical shell, alright, of radii r and dr, r plus dr, sorry, radii r, which is, you can say, the volume of the spherical shell, and the radii r plus dr will be how much? What is the volume of the sphere? 4 by 3 pi r cube. So here it will be nothing but we can say 4 by 3 pi r plus dr whole cube. Got it? And for this particular one r, it will be how much? 4 by 3 pi r cube. So what will I do is that this definitely will be more, r plus dr minus 4 by 3 pi r cube. I will do it. Alright, I will do 4 by 3 pi r cube. Clear? So if you neglect the term, that is dr square, dr cube and all these things, if you neglect this particular term, because it's very, dr is very small, so dr square if I do, dr cube I do, then definitely it will be still smaller. Got it? The probability density, got it, listen here, the probability density in this volume is obtained by multiplying the volume. The probability density, I said, you know, that is P, it is written by the radial probability density, we can say that. So it's the volume which is obtained by multiplying the volume with the probability function, which is psi square. Alright, the P, how do we get it? When we multiply 4 pi r square into psi square. That is called as the radial probability function, we can say that. Clear? Are you following, all of you? Alright, what I am saying here. So in this way, the function P is called the radial probability function. So when you will subtract it, what you will be getting it? You will be getting nothing but 4 pi, that is r square. This value you will be getting. When you will subtract it, what you will get? 4 pi r square dr square, you will be getting it. Isn't it? 4 pi r square. This one, this value. This one, 4 here, pi r square dr, you will be getting it when you will subtract it, neglecting dr square, dr cube and all those things, because dr is small, means dr square, dr cube will be still smaller, we can say that. So what is this graph is showing here, this particular graph what is showing? Same thing what I have shown it there, that when you are moving from that of the nucleus, what you can say, the probability distance is increasing from that of the nucleus for the 1s subshell. Alright, so you will find the maximum electron at distance of C here. The maximum probability, this is what? Probability function of finding an electron. So maximum where you can find the electron is at a distance of 0.529. After that what you will find? The distance is decreasing. As the radius is increasing, the distance is decreasing. Now if for this is 1s. Now for 2s what it will be? Here we will touch the node. In case of 2s, this will be the node. And again the graph will be this sort of, and again it will be in this way. So what you will find is that, what I want to show you here is that the probability of finding an electron is maximum when the distance is 0.529 angstrom. Then after that, as the distance of the nucleus is increasing, the probability again decreases. Decreases, and if it will be 2s subshell, 2s, then you will be getting a node here, because here it will reach and it will touch the origin. So here the probability will be 0. And again it is, the graph is going to rise further, we can say that. So the total distance, it is here nothing but r naught. Here the total distance for the 2s subshell will be what? That is nothing but 2 r naught. For the 2s subshell, where you will get the node? Nothing but 2 r naught. 2 r naught, this is r naught, this one is r naught. Then you will be getting a node will be there. For case of what? 2s subshell. In 1s subshell, no node is there. In 1s subshell is increasing. See here, the maximum probability is here. See here, this is the radial probability. I have already said you. So maximum probability here. What is the distance from the nucleus? See, this is the distance. After that, what you will find, that as r is increasing from the nucleus, distance is increasing. It is decreasing. Radial probability is decreasing. So what I said, this is for 1s, you can see. For 2s, it will touch here, and again the graph is going to increase. It will touch here means what is this? What is this point? It will be radial probability is 0. 0 means it is a node, and again it is increasing means again the distance is increasing. So what is the total distance now? This is R naught, this will another R naught, so it will be 2 R naught, it will be nothing but. Clear? Or 2 A naught, we can say that. So 0.529 into 2, we can say that. Clear? For 2s assumption. Similarly for 3s, again the same thing, the graph will be. So here what I am showing you, that is the thing I am showing you here, see. That is 4 pi, what I have written, sigma square and volume of the shell. So as the distance of the nucleus is increasing, the probability of finding an electron is decreasing. Alright, and the volume of the shell is also, what you can say is that it is increasing from the nucleus. The volume of the shell is also increasing from the nucleus. So it will reach a maximum volume, what you can say, the maximum probability it will reach at what distance? It will reach a distance when it will be 0.529 angstrom. Again, the probability of finding an electron is going to decrease. What I have shown you here, that is I have drawn it here. As the distance is increasing, listen here, as the distance is increasing from the nucleus, the probability of finding an electron is decreasing. The volume of the shell is also increasing. The volume of the shell, you can see, is also increasing. So it will be maximum. The probability of finding an electron is maximum at what distance? 0.529 angstrom. After that, again the probability decreases. So again, when the volume increases, the probability of finding an electron again is decreasing. So that is, it is being shown here. That as the volume of the shell, first when it is increasing from that of the nucleus, the probability of finding an electron is increasing. Then after that, again the volume further increases, the probability of finding an electron is decreasing. Alright, so in this way it is being determined that the 1s subshell is spherical, P subshell is dumbbell, D subshell is double dumbbell in this way. I hope you understood. Thank you.